M2. And we're gonna have the boundary layer here. Like that. It's exaggerated, but so here we have M1, M2.
Okay.
This is the real length. So this is L.
That's L. This is the real length.
Yeah. D is the diameter of the pipe.
Okay. So that would be that.
Yeah.
Okay.
Mm-hmm. So as we did for the A over A star, the very first problem we had, remember, we had something like that, and we said here that was subsonic. So necessarily this was subsonic to M1, but greater than M2. And we said we can imagine in that case that the float would be before, somewhere here. And we have the float here, then a higher subsonic, and then a lower subsonic at the end. So we imagine that the float was before.
Okay.
You remember that?
Yeah, that's actually what I missed on the GR.
Oh, yeah. So here that's the same idea. You can imagine that you would have stall conditions somewhere.
Okay.
So, for instance, if, like, for the homework, let's say, this is given, and you have to find this, yeah. And this is subsonic. So it accelerates, right, in subsonic, here. So that's going to be subsonic still, but more than that.
So they're both subsonic. It can't
Both
go supersonic with this.
Nope.
Okay.
No, because that's only converging. So at best you would reach Mach equals 1.
Okay.
But here, let's say, so that's a very particular case. Let's say we are in a random case. So we have here, it accelerates and we reach a faster subsonic value here.
Okay.
So you can imagine that Mach equals 1 would be farther somewhere.
Okay.
So you can do something like that. You can imagine a longer pipe with here M star equals 1.
Okay.
And so once you have this length from M1, from the point where you have M1 here to the point where you have M equals 1 sonic, this is L1 star.
Okay, now I get.
So
what
this
that
is the L star you read, because you don't directly read L star, it's n-dimensional, you read CF L star over D in the table for M1. That's linked to this. And now if you consider this compared to this, in the tables for M2, this is the length you would have. So this one here is L2 star.
Okay. Which is the length,
The
the imaginary length that you need to extend it to get
from
to.
M2
Okay.
to reach sonic conditions.
Okay.
Yeah. So in the homework they give this. It's 0.1. I'm not remember. Let me look. Point 6.
0.6.
They give P1, T1, diameter is given, CF is given. CF is given.
Where does CF come in? P1, do you know?
What do you mean?
Because you said we're gonna non-dimensionalize
Yeah, so
L.
since once you have this, once you have done this sketch, the question is what is M2? So what you can do first is calculate your 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 4 your 4 CF L over D, because all of these are given, and you would find something. Okay. Then if you look at the tables for M1 equals 0.6, you would find for CF, so let's write that. So at M1 equals 0.6 for CF L1 star over D equals 0.6. Sorry, not identical. Fanno. Here. 0.6. 4 CF L star over D is 0.4908. So if you do this divided by this,
You're gonna get L star,
times
L1 star.
L, or actually you don't even need this. Yeah, I'm trying to I'm thinking about the easiest way, the fastest way to do that. You don't need that actually. Once you have this, you can solve that for L1 star,
Okay, yeah.
because you know CF and D. So that will give you L1 star equals something. Based on this sketch, you expect your L1 star to be greater than the given L, which is 8 foot.
So is it always gonna be? Yeah.
Mm-hmm.
Okay. L1 star is always greater than L.
Yep. You will find 30 something. I don't remember.
Okay.
Once you have L1 star, you can calculate L2 star. So then, with this, let's go here. You calculate, because L2 star. Actually, I'm gonna write that here. If you look at the sketch, L2 star is simply L1 star minus, so that's not a 4, so that's L1 star minus L.
Okay. Yeah.
This, yeah.
Yes, I see that.
Yeah. So once you have L1 star, you can calculate L2 star. And once you have L2 star, you can calculate again for CF L2 star on D. Or yeah. You can do it like that, or from this you can subtract minus 4 CF L over D, and you have directly this. If you kept the 4 CF L over D here, but yeah, kind of the same thing. All this minus 4 CF L over D would give you this. Make sense? Because that would be 4 CF over D times L1 star minus L.
So you would, yeah, I see. Yes.
Okay. Anyway, yeah. The only to bracket good things with this, it gives you a physical meaning to the distance, and you would see how long would be the pipe to get to to back equivalent, but anyway. Once you have this, you read to the tables M2, the closest value corresponding to this.
Isn't there also some pressure ratios that we need to use?
After, yeah. So, but first you have to get M2.
Oh, because then it asks.
Then you read the tables at the same line and you get everything. So then for P2, T2, so for P2 you can write that.
So they have the. Hold on, okay, they have this stuff.
P over P star, P T over T star, PT over PT star. Yeah. So for P2 you can write that this is P2 over P star times P star over P1 times P1.
What's P star?
That's the pressure here.
So it's still a static pressure.
Yep.
At the end.
At here.
Oh, at the theoretical end.
Yeah.
Okay.
So this, you get this from the table at this. So that's why this is the first thing to get. The second one comes from the table at this one. And this one is given. That's 5 psi or whatever. So you get P2. And you do the same for T2 and you do the same for PT2.
Okay.
So it's not that complicated. Just this trick at the beginning.
Okay.
With the length.
Okay. And this is Fanno.
Yep.
With
friction.
What changes with rally?
So there is no friction, that's heat. So I can erase that?
Yes. I got everything. Thank you.
So let's keep the pipe here like that. We don't care about diameter anymore. Erase this. Oh, and the homework asked for a TS diagram.
Yeah. TS diagram. Yeah. We're just gonna go to the right.
To the right, yeah, but not to the
and down.
Down, so not to the end, not to the point where it's a star. You stop before here.
Okay. Well, do I know the point where it's a star?
So normally, it's like that. The Fanno line looks like this.
Okay.
And the limit is here.
That would be the star?
Yeah, because you can either start subsonic here, and at best you reach this, at Mach equals 1. Or you start subsonic, and you decelerate at best until here. So a TS diagram with a Fanno line like that actually combine the two possible cases, subsonic, supersonic.
Okay.
So subs here. Yeah.
So why does it combine the two cases?
Because it's practical to have both of them on only one graph actually.
The both rally and Fanno?
No. The Fanno, supersonic and subsonic.
Okay. Okay.
Because
why does it go from down to up?
where?
No. The arrow.
Okay, let's do that differently. So, with like in the homework with the subsonic case. So what we have, we can write that. So, most of the time, I mean every time in this course, for the Fanno flow, that's adiabatic. That's one of the assumptions. So we only have some SGen. And since we have friction in the boundary layer, we're gonna have some SGen, and so delta S is necessarily positive. Okay?
Okay.
So in the first case, if it's subsonic here, since the area decreases, the Mach is increasing, right?
Yes.
What about the temperature?
Static temperature goes down.
Yeah, because Mach is going up, right?
Mm-hmm.
So in the subsonic case, the Mach goes up, the temperature goes down, and entropy goes up.
Okay.
So if I want to plot the subsonic case, the temperature goes down, the entropy goes up, so I'm gonna go to the right and down, right?
Yes.
So if I start here, I would go somewhere here. So here, I'm gonna extend this. So here I have T1. And in the TS diagram we plot the isobars. So here I have P1, and I would stop at the end of the pipe here at P2. And here I have T2. Okay?
Okay.
So that's like that. And I'm going in that direction. And the limit case, as we said before, like in the homework, is I can accelerate up to Mach equals 1. So the limit case would be somewhere here.
Okay.
And here I would have P star and T star. Okay?
Okay.
So that's the subsonic diagram. Since it's adiabatic, the total temperature is constant. TT1, TT2, they are all equal. TT star. So I can draw a line here with TT.
Okay.
On this line, I can plot here I would have PT1. Not stop, sorry, PD1. That's the total pressure at point 1.
Okay.
Okay? And here I will have PT2, and here PD2, and here isobar, I would have PT star. PT is changing because that's not isentropic, because we have creation of entropy, right?
So entropy changes pressure but not temperature?
Mm-hmm.
Okay,
Total pressure.
Okay.
Total temperature is the same because it's adiabatic. Constant. Okay.
Yes.
So, if you look here, the difference between the static and the total temperature here, it's related to your Mach number, right? So since this line is still the same, the total temperature, you can see that here this distance is increasing, which makes sense because that's subsonic and that accelerates. So the Mach number increases. Up to this point, that's the maximum case where Mach equals 1.
Okay.
That's the subsonic diagram. Now, if you have this thing, but now if you are supersonic here, supersonic converging, the Mach would decrease, right?
Yes.
If the Mach decrease, the temperature
Will increase. Static
will
temperature.
increase. So if we do the TS diagram for the supersonic case, so this is subsonic. Now for supersonic, so I would have TT still here. So we said Mach goes up, Mach goes down from supersonic to 1 at least. That would be the last case. So Mach goes down, temperature goes up, and entropy still goes up because of the friction. So if temperature goes up and entropy goes up, I'm gonna go to the right and
No.
to the up.
Okay.
So the same thing, but with subsonic case for M1 would look like that. So I would have T1 here. I would go like that. T2. Okay?
Yes.
Up to the particular and limit case, which would be here at T star when M equals 1.
Okay.
And again, you can see here that I would have PD1, here PT2, and here PD star, as well as here I have P1, here I have P2, that's my isobars, here I have P star, okay?
Okay.
Again, you can see that the difference between static and total is decreasing because my Mach number is decreasing, so that makes sense. So actually, instead of representing this if we have the supersonic case or this if we have the subsonic case, we represent the whole thing.
Okay.
So what we represent is this combined with this, so that we have all the information. So that's why we go like that. We draw a full line like that with the star conditions here. And we know that in that case, we have here the supersonic case and we have here the subsonic case.
Okay.
Does that make sense?
Yes.
And this line is the Fanno line.
Okay.
So in the homework we do just this. We don't
Okay.
reach the sonic condition, and this is just represented, but it's just in case of we would have had the supersonic condition at the beginning. That's the
Okay.
whole thing.
Okay.